Hi, my name is Chang. On behalf of my co-authors, I would like to present our research on gesture-based interaction between autonomous vehicles and pedestrians. With the development of autonomous vehicles, effectively communicating and interacting with other road users in traffic is challenging for them. Considering the safety of pedestrians, pedestrians need to obtain notification of the intentions of autonomous vehicles before the car passes in front of them. Compared to traditional cars, autonomous vehicles lack certain communication methods with other traffic participants. Therefore, autonomous vehicles must interact with other traffic participants to determine the right of way and communicate the vehicle's intentions to ensure safety. To this end, external human-machine interfaces (eHMIs) were introduced into autonomous vehicles to provide the capability to convey important information to external traffic participants in their surroundings. Common eHMI include lighting-based eHMI, text-based eHMI, and projection eHMI. Lighting-based eHMI utilizes LED lights and indicator lights to display the vehicle's status or intentions externally. Text-based eHMI uses onboard displays to show text information to pedestrians, such as stop, don't walk, or you go first. Projection eHMI can project warning signs or pedestrian attention prompts on the road or sidewalks around the vehicle. For example, projecting zebra crossing to enhance pedestrians' awareness and understanding of autonomous vehicles. Nevertheless, the effective implementation of interaction between autonomous vehicles and pedestrians is still worth worrying about since pedestrians may not even notice that they are involved in interaction with an autonomous vehicle. Now, let's watch a video.
Go. You go first. Okay, you wait in place.
Gestures are a common method of traffic communication, improving driver-pedestrian interaction. Drivers can use gestures to communicate the vehicle's intentions, such as turning left or right or stopping. Pedestrians also commonly use gestures to signal drivers to stop, indicating that they are about to cross in front of the vehicle. Additionally, gestures are one of the ways traffic police officers use to direct traffic, and there are easily understood gestures in sign language for expressing walk and stop. However, gestures have received comparatively less attention as cues to be referred to in existing designs and research on eHMI, especially compared with lights and text. We aim to compare the relative effectiveness of gesture-based eHMI with other eHMI. Additionally, the study seeks to identify the most suitable gestures from a wide range of popular gestures to provide valuable insights for the design of future eHMIs designed for autonomous vehicles. Therefore, our research questions are as follows. Question 1. What are the differences between the effects of eHMIs? Which gestures work best? Question 2. What underlying factors contribute to this difference? To answer the above questions, we conducted a virtual reality experiment and a following online survey. But before doing these two studies, we must choose the appropriate gesture to be tested. We carried out a process of selecting suitable gestures which involved 3 stages. In the first stage, the researcher gathered gestures and created a gesture library. In the second stage, the gestures were evaluated and screened by a panel of 6 researchers. Step 1 was to categorize the gestures semantically. Gestures were classified based on their meanings, falling under the yielding or non-yielding category. Step 2 was to perform a duplicate merge. Familiar gestures in key areas were combined and categorized together. Step 3 was to conduct a cultural screening. The study evaluated familiarity of gestures and eliminated those that were deemed too culturally specific. In addition, the politeness of gestures were considered, and those with offensive meanings in certain cultures were excluded. Step 4 was to screen for clarity of gestures. See the supplementary material for sources and the screening of specific gestures. After the panel screening, for yielding gestures and for non-yielding gestures were selected. Next is Study 1, Virtual Reality Experiment. We designed a city scenery that closely resembles the real world. Pedestrians will encounter autonomous vehicles at a crossroad. There are zebra crossings at the intersection, but there are no traffic lights. Pedestrians need to understand the intention of the autonomous vehicle and cross the road. The generated positions and behaviors of autonomous vehicles are standardized. We meticulously designed the motion behaviors and the transition point of autonomous vehicles, making it challenging for participants to infer vehicle intent through implicit information. During a round of experiment, participants press button to walk to the starting point according to the instructions in VR. In the meantime, autonomous vehicle was generated and approaching the crossroad by the left side of the pedestrian. Participants need to judge the vehicle intention according to the eHMI information designed in the experiment and decided whether to go before the autonomous vehicle. When pedestrians arrive at the ending point of the crossroad, a crossing is considered to be completed. Participants need to answer the questions orally at the pop-up windows. Participants can press button to control the pedestrian to go to the next intersection after finishing the questions. Semi-structured interviews lasting no more than 30 minutes were conducted after the whole experiment. This study used a within-subject design. We performed a two-way repeat measure ANOVA for analysis to investigate whether there is an interaction effect between different eHMI designs and the encounter times. The 12 eHMI designs include 8 gesture-based eHMIs, 4 yielding gestures, and 4 non-yielding gestures, 2 light-based eHMIs, 1 yielding and 1 non-yielding, and 2 autonomous vehicles without any eHMI. Pedestrians will encounter each eHMI 3 times, and the order in which the eHMI designs appeared was randomized. Dependent variables include error rate, difficulty in comprehension, perception of danger, duration of observation, and duration of hesitation. The results are as follows. For yielding vehicles, on the difficulty in comprehension, the duration of hesitation, and the duration of observation for yielding vehicles, the critical findings was a significant interaction effect for eHMI designs and the encounter times. The Y0, Y2, Y3, and Y4 are significantly easier to understand by participants than Y1 and Y base. Compared to autonomous vehicles without eHMI design, implementing Y0, Y2, Y3, and Y4 significantly reduced observation time and hesitation time. However, the application of Y1 results in even longer observation time. What's more, the difficulty in comprehension and the perception of danger with Y3 is the lowest, regardless of the number of encounters. The level of comprehension difficulty for Y0 exhibits an approximately linear decrease, but for Y2 has an upward trend with increasing repetitions. The duration required to figure out the intentions of autonomous vehicles with Y2 is minimal during the initial encounter, but it gradually lengthens during subsequent encounters. When considering the overall performance of the 3 encounters, it can be observed that Y4 shows the most pronounced learning during experiencing. For yielding vehicles, a significant main effect was found between designs on the difficulty in comprehension, perception of danger, duration of observation, and duration of hesitation for non-yielding vehicles. The N0, N1, N2, and N4 designs were significantly easier for participants to understand compared to the N-based design and result in significant improvements in participant perception of safety when implemented on autonomous vehicles. As compared to autonomous vehicles without eHMI design, the implementation of N2 and N4 is significantly helpful in shortening the observation time. And then, N4 is the most easily understandable eHMI design for pedestrians. For the second and third encounters, N1 is regarded as the most secure eHMI design for pedestrians. N4 requires the shortest duration of observation. The duration of hesitation when meeting with autonomous vehicles equipped with N3 is noticeably lower compared to other counterparts. Nevertheless, it does not imply that N3 is the most effective. In contrast, pedestrians often misinterpret the non-yielding intention of autonomous vehicles equipped with N3, leading them mistake. The previous virtual reality experiment convincingly demonstrated the feasibility of utilizing gesture interaction in autonomous vehicles and pedestrian interaction scenarios to receive a broader range of viewpoints from the population and to gauge the acceptance of gesture interaction in a wider context. we conduct additional research utilizing an online survey, building upon previous experiments. This questionnaire categorizes gestures into 3 dimensions for evaluations: clarity, familiarity, and pilotness. Additional information on questionnaire design and analysis can be found in the appendix. After analyzing the data, we obtain the participant rating for each gesture. The image below shows the rating of the different gestures and the differences between the 3 rating dimensions of the gestures in the different age groups. Now, I want to discuss with you the most critical findings of our research. First, when compared to gesture-based eHMI, lightning signals lack clarity for message receivers. This is because lightning applications are common in daily life, making light signals less distinct for pedestrians. Some participants even mistook the light eHMI on autonomous vehicles for status, indicators, or signal for other vehicles. In real-world situations, vehicle lights from a distance often struggle to capture pedestrians' attention. The clarity regarding the signal recipient is paramount in the interaction between pedestrians and autonomous vehicles. Second, people often associate specific signals with particular meanings over time, leading to confusion when new meanings are introduced in different contexts. For example, traditional association with colors like red lights for braking can conflict with other meanings like standby or inactivity on artificial objects. Gesture exhibit complex overlapping semantics, with some gesture like Y1, Y2, N1, and N4 being easier to understand due to interconnected meanings related to vehicle intent in traffic scenarios. However, gestures like N3 with diverse meanings like hello, goodbye, and no can be exceptionally confusing and lack a fixed interpretation in traffic context. The importance of avoiding pedestrian misinterpretation of vehicle intentions stems from the potential overlap in semantics between gesture and lights. Third, study findings indicate that gesture-based eHMI affects the pedestrians' success rate and perception of risk during intersection crossings, making them feel safer. Pilotness in gestures is crucial, particularly for specific age groups, with gestures like Y3 and N1 receiving high ratings. The use of gesture-based eHMI facilitates interaction between pedestrians and autonomous vehicles by creating an anthropomorphic agent that conveys AV intentions and engages in mutual exchange with pedestrians. This approach enhances pedestrian safety and builds trust due to the familiarity people have with real driver in traffic scenario. Finally, different eHMI exhibit varying learning cost and learning rate. Familiar eHMIs have lower learning cost, leading to better performance during initial encounters. For example, light-based eHMI, similar to standard traffic light, result in shorter hesitation times. During the first encounter, similarly, gestures commonly used in daily life are grasped more swiftly, such as Y2, which exhibited the shortest observation time in Study 1. Concerning learning rate, light-based eHMI mainly conveys intentions through colors and logo animations, fostering stable learning and memory of abstract graphics associated with vehicle intentions. Even unusual gestures have the potential to be rapidly learned and accepted. Take Y4 as an example. Despite its initial lack of familiarity, it impresses pedestrians due to its straightforward and easily recognizable characteristics, coupled with instructions that lack overlapping semantics with the direction of pedestrian movement. So thanks so much for listening, and please read our paper for more details about the statistical method, qualitative findings, and discussions.